Okay, welcome everybody. Come in and sit down. I'm just going to take a picture of you all. There we are. So my name is Ben Evans. I am a senior principal software engineer at Red Hat, although this is actually the last time I'm going to give a talk as an official Red Hat person, because we're moving to IBM. Like Red Hat is part of IBM, but they're actually moving us into IBM proper. So I'm not going anywhere, and neither is the work I'm doing, but I felt it was kind of, a little bit melancholy for this to be my last talk as a Red Hatter. Never mind. So the title of my talk today is Java 24 a functional programming language? For those of you who haven't met me before, I work at Red Hat at the moment. Before that, I worked at New Relic, where I was lead architect for instrumentation. I also founded a company called JClarity, which we sold to Microsoft. And I've done a bunch of other things in banks before that. I live in sunny Barcelona these days, but I spent a lot of time living in London, where I helped to organize the London Java community, which is one of the largest and most successful jugs in the world. I have a couple of books which are out at the moment. These are my latest books. And we're actually going to have a book signing immediately after this talk. So if you're interested in some of the ideas that I'm going to talk about in a minute, then please come to the area by the check-in desks. So up there, basically at the back of the auditorium, and I will be lurking and handing out and signing copies of my books. It's first come, first served, so please come after the talk. Okay, so with the preliminaries done, let's get into what I want to talk about today. And before I even really start talking about anything particularly technical, there are three principles that I want you to have in mind throughout what I'm talking about. And these are, I think, principles that I try to use and try to apply all over software, especially to things like performance, but I think they also fit very nicely for the topic of the talk today. And the principles are outcomes, not mechanisms. The point behind this is that we sometimes over-rotate to thinking about a specific technical mechanism versus what the outcome actually is. So, for example, Holly is always a tough act to follow, but one of the things that she spoke about in her keynote, which was excellent, is how Quarkus moves things from the runtime phase and the startup phase into the build phase. That's a great example of where people were kind of focused on the wrong thing. People were saying, we need native compilation. Native compilation is a mechanism. The outcome is to reduce startup time and also to reduce wasteful repeated computation. So you might use the native compilation to help you achieve that, but you need to stay focused on the outcome. How does that relate to functional programming? Well, you need to think carefully about whether functional programming is an outcome or a mechanism. And if it's a mechanism, what is the outcome you're trying to achieve? So I'm just going to leave that one there and let you think about that. The next thing is, does it matter? This is kind of connected to outcomes and mechanisms, but does it matter is always an extremely important question to ask. Sometimes things that we can get fixated upon as technologists actually don't matter. If you are determined to drive down the average time that your microservice responds in, well, what if that's not the right thing to be focused on? What if what actually drives people away from your app and causes you to lose customers is not the average, but the 95th percentile, the outlier performance that's actually more important than the average overall? It might be the case that for your customers, people are very prepared to tolerate a bit longer average delay, providing there are no massive slowdowns. So focusing on what matters and determining what matters is also important. Again, you'll see how that applies to functional programming in a minute. And then, of course, the perfect is the enemy of the good. You'll see this one again and again as I go through the rest of my talk. But before we start, I just want to do a couple of things. So hands up, I'm just curious about this. How many people are running Java 21 in production? Oh, good. We have some early adopters, I see. And 17? 11? 8? Anybody running something before 8? No, nobody's prepared to admit to it. Good. And anyone running a non-LTS version of Java in production? One person. There we are. That's about what I was expecting. I just like to have these numbers. That's good. It's a nice, healthy number of Java 21s, I see. Okay. And then another thing, this is something that matters. So here is a QR code. One of the things that I'm doing at the moment is I'm working with a code school based in Barcelona, and we're having a funding drive. And I'm actually going to personally match all donations up to the first €1,000. So if you scan the QR code and you donate during this talk, I will match anything you put there from myself. Okay? Let's see if we can make this the most expensive conference that I've ever attended. Okay, so now let's get into the meat of functional programming. I gave a version of this talk in 2022, which is available online. I didn't actually give it here at JNation, because last year was the first time I actually came. So in that talk, I basically came up with this concept of a scorecard. What do I mean by a language when I call it functional or not? And then I want to talk about some other things that came out of that talk, specifically the collections, Java's type system, and Java 17 features. And these are sort of some of the underpinnings that I'm going to talk about and when I talk about what's changed in the last 3 years. So what makes a language functional? Does anyone want to give me their definition? You'll have to shout, but I'll repeat it for the tape. Anybody? No? Some people might guess, like, functions as first-class values. That I can take a function, a bit of code, and I can manipulate it as though it was a data item. Yeah, you'll notice I'm being kind of loose about my terminology here, because I'm not necessarily just talking about Java here. I could be talking about Lisp or Python or any other languages, right? And yeah, sure, that's true. You cannot do functional programming unless you can represent a function as a data item, but it's table stakes. It's a necessary condition if you're a mathematician, but it's not a sufficient one. So what does make a language functional? And here's where I think it starts to get interesting, because I think that functional programming, like object-oriented programming, it's not a question of a hard and fast, this language is, this language isn't. It's more of a sliding scale. Languages have features which enable functional programming, more or less, and which are associated with a functional style and a functional way of thinking. Some of them have more, and some of them have less. So here's my list. Here are a list of 7 properties, and I've given Java a score for each one. So pure functions, functions which don't have any side effects, functions which are genuinely equivalent to mathematical functions. Does Java have those? No, not really. I mean, sure, you can write some, but it's actually very difficult to confirm that they are genuinely pure, and you certainly don't get any help from the compiler or the runtime or the platform. So that one is a big no. Immutability, sure, you can write immutable code in Java. Not very easy, because you have to write final everywhere, you have to understand what it means, you have to understand the memory model. So that one, it gets a tick, but only just. That one is kind of a scraping through. What about higher order functions? Well, yes, you can certainly do those. Since Java 8, we have Java util function. You have a function type, and as a function type, a method can return a function, or it can take a Java util function as an argument or as a return type. So higher order functions, yes. There is a caveat to that, which I will come back to later. But in general, to a reasonable working definition of higher order functions, Java has those without a problem. So that's another tick. Okay, so we're up to 2. Tail recursion. Now this one you might be aware of, or you might not, but Java does not have any native support for tail recursion. If you write a tail recursive definition of factorial in Java and run it, you will get a Stack Overflow, because the tail recursion is not optimized away by either Javac or by the Java virtual machine. That is a deliberate design decision, which dates all the way back to Java 1.0, and it's maintained for backwards compatibility reasons. Not because they didn't know that it was possible to optimize it away. It was a deliberate decision that what you wrote in the Java code is exactly what would be represented in the bytecode. Other languages, Scala and Kotlin, for example, both will see the tail call in final position and will optimize the tail recursion away. So if you write the same thing in Scala or Kotlin, you will not get a Stack Overflow exception. You'll very quickly overflow the size of a long, but that's a different problem. So that is very definitely a big red mark there. Yeah, there's not much you can really do about that. There have been various attempts to try to see, can we do something at the bytecode level and basically provide a hint, like that this method needs to be tail recursively optimized, but it's never really gone anywhere. Okay, so what else have we got? So we're now 2 for 4. What's next? Closures. Does Java have closures? Well, yes. Again, depending on who you talk to. There are people in the Lisp world and in other places who would argue that Java's closures aren't really closures because they don't allow you to access mutable state. But that is a technical distinction. And in Java's case, we would expect any complex state to be represented as an object anyway, rather than a single value. So I'm going to give Java a pass on that one. Okay? Now, the two last pieces of this, laziness, having lazy evaluation of a value, Java doesn't do at all. It's almost impossible to do in the base language itself. You can do some very sketchy things with class loading and use the laziness of class loading to do certain tricks, but it's really pretty horrible. However, there is something that I could say about that later, which I will do. And then finally, things like currying and partial applications. This is where the idea in a language where if you have a function which takes 2 arguments, you can supply one of the arguments and it will automatically be converted into a function of 1 argument. Java doesn't do anything like this. The by-function interface has no support for this out of the box, and it would be pretty limited even if you did. Okay? So you can add other properties to this, I guess, or you can debate whether some of these are really necessary to be thought of as functional. But this is a reasonable list, I would say. So we have got a final score for Java of 3 out of 7, maybe a couple of other bits and pieces as well. So let's give Java a pass because it's JNation and say 4 out of 7. Okay, so that's where we were as of Java 11 before Java 17, say. We can go on, and in a second I'll talk about how things are changed when we go to Java 17, but there are a couple of other things that I want to specifically highlight as difficulties that Java has with functional programming. And always remember, the backwards compatibility of the language, it can be a major hurdle. Java does not break things which already work. That's particularly true with the Java collections. The Java collections date all the way back to Java 1.2, which was 27 years ago, and they are not changing in any fundamental way. Certain things were added to them in Java 8, but that we needed to bring in default methods to do that. We couldn't just add new methods to the collections, and we certainly can't take anything away. Related to the collections, there are also 2 other things which are, sometimes in functional languages, people talk about everything as an expression or everything as an object. Neither of those statements are true in Java. Java does not, as it stands right now, have a single-rooted type system. There are primitives. There is the tree of types, which starts from object, and then there are the isolated dust-like points, which are the primitive types. There is no unification of that at type level. There are some nasty auto-conversion hacks, but that's it. Secondly, not every statement is an expression. Java has the void keyword, which indicates that a method does not return a value. Technically speaking, what it actually means is that in the bytecode, when the method exits, the evaluation stack of the method is empty. That's actually what it means. But that has its own problems. It causes issues with reflection and other things. But the fact that we can't model every statement as an expression means that certain aspects of functional programming become more difficult. It shows up in the streams APIs as well, and all sorts of things. But hey-ho, we are stuck with it. That is not going to change. Okay, so what about the collections themselves? Well, there are a number of problems with them. They are large interfaces. I don't know if you've ever done this experiment where you just try to implement, let's say, a dictionary class. So this is just a map of strings to strings, and you want to implement it in a simple way, which looks like a classical undergraduate hash map. There's a lot of methods. So if you like, class myDict implements map string string, and then let IntelliJ auto-generate, and you end up with like 10 pages of code where it's written stubs for every method that's in that class. And that's a problem. One of the major problems with it for functional programming is that it also includes methods which mutate the collection in place. Now, in functional programming, you don't do that. What you do, if you have a functional collection, is you want to make it immutable, and if you add an element to it, you're not actually adding an element by mutating the collection you have. You are creating a new collection, which is the old one, with something added to it. And whether you do that by making multiple copies, or whether you do some smart internal data structure, which keeps track of different versions of it, that's up to the implementer. But Java doesn't do that. We have mutating methods. Okay, so what does that mean if we want to have an immutable collection in Java? Well, there's nothing at type level which says a collection is mutable or immutable. They both show up as a collection interface. And those collection interfaces have add and delete on them. So what do you do? What do you do if your method is expecting a list, you get passed in a list, and inside your method you call add on it? Right? Well, the compiler's not going to save you, because there's no type information to say you can't call add on that. So what you are forced to do is to use what's called the unsupported operation exception hack. Basically says if you are an immutable collection, if someone calls a mutation method on you, throw unsupported operation exception, which is of course a runtime exception. So it doesn't show up in the signature of methods, which is fantastic, because now you absolutely have no way of knowing, if you are writing library code, whether someone at some point later will attempt to pass you a collection. So you have to defensively copy if you want to be safe. There's more to that story. I could rant for some time about the decision not only for list of to be immutable, but there is a method, an implementation which is also called ArrayList, which is buried in the collections interface. So, and if you call methods on that, they throw unsupported operation exception. But the name of the class is ArrayList. Just shockingly poor design. Holly might be right that naming may be the hardest problem in computer science, but there's hard problems, and then there's deliberately shooting yourself in the foot. Okay, so that's not great. We've got issues. We don't see the mutability in the type system. They're not designed for functional operations. When we do iterators, you do things like the iterator moves through the list. But if you look at the element that comes out of the iterator, you have already modified it and effectively split it into the item and a new list with a new head. Well, what happens if that doesn't work and you want to back the operation out? You can't. So the whole style of this is not suited for functional collections at all. Okay, we have streams now. So that's great. Why don't we use those? Problem is the collections are first class. They're everywhere. Backwards compatibility, we are not getting them out. So you can't just use streams everywhere because they're not supported on all of the JDK methods which are there. In addition, Java has no equivalent. We have iterable, but we don't have a traversable interface. So there's no way of doing what we can do in Scala, which is just to say this is traversable and using internal iteration like we would for Lambda expressions. There's also the fact that containers are very much not functional containers. They don't have map and filter and reduce and methods like that. Streams do, but only to a limited degree. They're not true functional containers. There's also the point that, unlike in functional languages, the streams that we see in Java are ephemeral and consumable objects. They are not stable, they are not supposed to be long-lived, and they're not supposed to be passed around. You can, argue about things like, I think Spring JDBC does this, where if you have a reactive or non-blocking JDBC connection, I think some of those were implemented as streams. But I have some severe doubts about that design. Anyway, come and talk to me about that later if you want. So, okay, let's just summarize the type system. So here is, if someone said to me, Ben, describe the type system of Java, this is what I would say about it. I would say it's static, it's strictly nominal, it's object imperative, it's type erased, modestly type inferred, and it's slightly functional. Right? I think that's a pretty good summary of how we feel about it. It's not, pedantic. It's not particularly, designed to prove any particular point of purity. It is practical, and is it good enough? Yeah, I kind of think it is. The principle that the perfect is the enemy of the good, that runs all the way through Java. Java is designed to be a stable and robust language for building business applications by developers who want to go home and see their kids or partner or cats at the weekend. Right? So the fact that the type system reflects those practicalities is not a surprise to me. But to touch on a couple of them one by one, it's very static. The type system is enforced by the language and by Java, but the JVM is quite dynamic. The JVM has this idea that we're going to use the analysis on the class files to check that they aren't doing anything horrible. There is only a single entry point which accepts a class file and nothing else. And that provides additional checking which helps enforce the runtime behavior. So a modern JVM looks like this, and this is sort of on the left-hand side, we've got the Java programming language and the staticness of that. And then we have this very dynamic runtime. This is what Holly was talking about earlier when she talked about whether we need to pay the efficiency cost of this extremely sophisticated and extremely powerful and performant JVM. But it comes with a lot of complexity, and maybe we're paying for things that we don't need. Okay. Also, in my list of what the type system was, there was one adjective I didn't use. Strong. That's because strong typing doesn't mean anything. I like this quote from my old buddy Curtis, who once said that strong typing, all it really means is that the person that's speaking likes the type system that's being discussed. Doesn't have any technical meaning at all. A static type system, it means once variables have a type, you can't put the wrong sort of data in them, right? That makes sense. But strong typing doesn't mean anything. So Java's types are also nominal and only nominal. You can only be compatible if an explicit inheritance exists, whether that's class inheritance or interface inheritance. There is no way of talking about types except by names, at least for L values. And if you define these two types, pair and tuple2, they have nothing to do with each other. There is no automatically generated conversion between instances of pair and tuple, even if the generic types match as well. This is related to the fact that there are no type constructors, if people know what type constructors are, but I'll mention those again in a minute. It's object imperative, it's a simple OO model. Primitives are there because it simplifies a lot of things, and also because in the 90s, they were much more performant on limited hardware. The syntax of C is also very much governed by C and C++ to basically trick those devs into believing that Java is very similar to C and C++. It is not. Type erased. We remove the knowledge of certain aspects of Java's generics at compile time. The erasure exists for backwards compatibility reasons, and there's this sort of raw types provided as a back bridge. People often complain about type erasure. Hands up if you hate type erasure. normally there's at least a few people who hates the idea that their generics aren't available at runtime. But a lot of the time what it actually is people want a list of int, and they don't like the fact that you have to have list of integer rather than list of int. Okay, so to turn back to functional programming, Java is not that functional. Is it enough, though? There are some things. There are no higher-kinded types, which is what HKT stands for, which is the type class pattern or the type constructor. This actually affects higher-order functions. So the idea of a higher-order function actually loses some type safety because of type erasure. But it's at that point in the type system that it causes a problem. It's not anywhere else. The things which are provided on Java Stream are not, if I say monadic or monad. Hands up if you know what a monad is. About 3 people, okay. Should probably take that off the slide. But without that, that is, again, it's the does it matter question. People will use, if I said, do you know how flat map and optional work? Yeah, let's try this. Hands up if you know how flat map works on Stream. There we go. And optional? Yeah, okay. So in fact, you probably do know what monads are, at least intuitively, even if you've never used that word before. Probably do a talk on that at some point. Anyway, so we basically end up in this place where we've got some stuff. Is it enough of what developers need? I think so. I think a lot of it is aligned with what mainstream Java programmers have wanted. And the thing about it is, it hasn't stood still since Java 8. It's been getting progressively better and better since then. So for example, with Java 17, which hopefully most people are now using, it's kind of weird. Java 8 was like, I always call it like the Windows XP version of Java, because Windows XP hung around for like years after it was supposed to. But now what I see is that people are moving directly from Java 8, and in a lot of cases 17 is the new baseline version. So I think I can share these numbers, I think. So based on what I can see from customer data at Red Hat, most of our customers, even 6 months ago, Java 8 was still very much the single biggest version. It was under 50%, but it was like 45% of the market. And now what's happened is Java 17 and Java 8 are now about 35%. And then Java 11 is down at the sort of 22-23% level. So we've gone from a place where Java 8 was ahead to everything being kind of in the middle somewhere, and now Java 11 is definitely falling away, and Java 17 is going to break through into the lead. So that's cool. Java 17 is a nice version. One of the things that I like about it are switch expressions. You can do a couple of neat things with them. They must have total matches, but they have a default. If you don't do a default, you get compiler errors. You also have these things, algebraic data types. So this is a combination of 2 features, sealed types and records. Hands up if you're using sealed types and records. Yeah. Hands up if you have gone back and have retrofitted your code bases to take out things which used to be classes and are now much better off as records. Okay, so that might be something for other people who haven't done that to try. I think that there's a lot of low-hanging fruit. We're going back into the code base and just stripping things out. And at first, it feels a bit like donkey work, but when you go back and actually do it, you find that actually, oh yeah, this is actually making things a lot easier to work with. The other half of algebraic data types are sealed classes or sealed types. These are great because they actually provide you with an ability to control the interfaces which are, the implementations of the interfaces which are present. There can be problems with things like testing, where you need to do mocks, which you might not have previously needed to. But I tend to find that actually I'm writing a lot of sealed classes. These also play into the next major feature that came out in 17, or at least the first version of it, which is pattern matching. So the only version of this that's in Java 17 is X instance of pattern. And this seems like it's not very important, but this is one of those things in Java that you see again and again. Is quite often there is a small feature which appears in one version. People's like, that's not that important. Why are people making a big fuss about it? And then things get built on top of it. So the classic example is invoke dynamic, which was added in Java 7, and at that time, Java 7 wouldn't even emit. Java would not emit an invoke dynamic. If it encountered some bytecode which contained invoke dynamic, it would happily execute it, but it would never create any of its own. Now, vast amounts of modern Java is built on invoke dynamic. Lambdas are built on invoke dynamic. Default methods, records are built on invoke dynamic. String concatenation these days is built on invoke dynamic. But you never would have guessed that by looking at this tiny acorn from which all of these things have grown. So Java 17 pattern matching seems not very impressive. It's saved an unconstrained cast and tidied the code up a bit. Wow. So you can, instead of doing this, you can now do this. You've got a pet, which is either a dog or a cat, which comes from here. And now you can treat these two differently. Okay, so let's move on from 17, because I've only got another 20 minutes. So what happens next? Well, we enhance pattern matching with the new Java 21 version. We pick up some other bits and pieces on the way, and then we'll talk a little bit about string gatherers and a little bit about virtual threads. So the first thing is, we take our pattern matching, we move it on from simply instance of, and now we can use it in switch. So we can do things like having a switch statement which switches on a type. And that includes these neat things like guard expressions. So here we're checking to see whether the pet is a dog or not. And there are now 3 outcomes, because if the cat is feeling like today is Monday, it's going to lie to you, and it's going to tell you it's a dog. And that's what is happening with the when clause there. The rest of the week, it's going to tell you the truth and say, no, I'm not a dog, and the dog will tell you true as well. Okay, so that's a simple usage of a guard pattern, which we can do with the type here. So again, rewriting some code to put it into this form, and I would also take the opportunity to see if any existing switch statements, which are in the old C-like style, if you can remove them. Part of the perfect being the enemy of the good pattern is to start removing things and to start cleaning things up to move them into a form, and there is incremental benefit. When you are working through it, you might not think that you've gained that much, but then you look back at the code and you realize that a lot of this is cleaner and more effective. People also talk about data-orientated programming, and what they mostly mean is reordering and reworking things to deal with records and sealed types. Related to these, we also have what are called record patterns. So remember how a record is defined? You just have the name of the type, which is like a pet or a dog or whatever, and you can embed things like this. So from here, I don't actually care about the dog instance at all. All I want to do is extract the dog's name. So I don't even have to declare a variable name for the dog. What I can do is I can just reach inside it and take the variable out of it. Now, who's seen this type of pattern in JavaScript? A few people, yeah. So this is what JavaScript and a few other languages, Python, might call destructuring. And it works in Java because records have explicit deconstruction semantics. General objects in Java do not, because of serialization and a whole bunch of other nasty stuff connected to that. But when records were introduced in Java 17, the way that Brian designed them was so that they would have explicit construction and deconstruction semantics. So this was in the back of people's minds when records were introduced. Okay, let's do a couple of quick examples of a slightly more complex. So we've got our pet again. We've also got A, B extends A, and a generic pair class as well. Okay, So here we have how the pair is going to get matched. So we've got A1 and A2. So what we know is that P1 is a pair of A. So they are either an A and a B, or a B and an A, two A's or two B's. So we do the standard trick of checking the most likely to be false case first, which is that they're both the subtype, so in which case we check them directly, and then we do the A and the B checks, and then the cross check. A couple of things I've commented out the case null and the default here. That is because the behavior with switch statements and expressions has changed with null. In previous versions of Java, if you put a null into a switch expression, you get a null pointer exception. So you have to do an explicit pre-switch statement check for the null. For what we're trying to do with the harmonizing of switch and the rebuilding of it, that becomes a problem. So you're now allowed to explicitly have a case null check. Equally, you can also have a default, but a default does not match null. So if there's any possibility that the incoming thing you're going to switch on is null, you should check with it with case null. And then we have another couple of examples here where we're just deconstructing as well. Java 22 also introduces the unnamed variable and the unnamed pattern. For those of you who may remember, you used to be able to use a single underscore as a variable in Java. You no longer can. It was disallowed, I think, back in Java 11. And now we are in a place where the single underscore has been reintroduced to be an unnamed variable or unnamed pattern. It's where you don't care about the value, so you just enable you to concentrate and focus your thinking. If I don't need it, just call it underscore and focus on only those things which matter. I'm mostly talking only about final features here. I'm going to mention this one, the primitive pattern, because it's still in preview. It will still be in third preview in Java 25. Why is this important? Why are we doing this? Well, we want the Java type system to move towards being more uniform and more single-rooted. This is another building block, and I'll talk about it in the final part of this talk. Very quick slide on stream gatherers. So this is something which came out in Java 24. This is a big missing piece of the stream API. In previous versions of the stream API, you have intermediate operations, so lazy and eager. And most of the time, with things like filters and maps, these are intermediate, lazy operations, where data will flow through them, but there is no point at which you have to collect all of the data together. And then at the end, you have toList or collect or reduce. They are terminal operations, and they require all of the data to come through. There are exceptions to this. So, for example, sort needs to see all of the data before it can decide which order to emit things in. So sort is an example of an intermediate, eager operation. But they're generally rare. Gatherers provide a fairly sophisticated way for you to create custom intermediate operations. So you can go beyond just creating a second, like a stream of a stream. You can go beyond what you can do with FlatMap, but you can generate a completely custom intermediate operation rather than having to rely on what's provided in the standard API. You can sort of think of it, if you're used to link from C# or from SQL, as kind of being like a group by. Okay, very quickly about virtual threads. So essentially this is the standard thread lifecycle. Threads can run to completion, but more likely they will hit either a sleep or a wait. They'll be swapped out, or they will hit an I/O operation. And what virtual threads do is they create a new type of thread, which is managed by the Java virtual machine, not the operating system. The OS cannot see virtual threads. They are just Java objects. And the way it works is, you didn't know this, but between Java 11 and Java 17, the entirety of the Java socket API implementation was rewritten. Inside Java 17 sockets, you are now using non-blocking API I/O, even if you call the blocking API. It's only the API that's blocking. The implementation is now always non-blocking. So what this means is if you do a blocking operation on a virtual thread, the non-blocking I/O is dispatched and the thread is freed up. Okay? So this basically gives us the ability to do things like Go routines, and yeah, they're also similar to Erlang processors, and that is the basis of some of the concurrency that we're going to build on top of it, which is useful for functional programming. Yeah, every time you make a blocking I/O call, it yield. I said that. They're most similar to Go routines. Other async await approaches were considered and rejected. I think this is one of the good examples of where Java commitment to thinking things through properly and trying to make sure that the final feature is as good as possible rather than just do what other languages are doing. I look at a language like Rust, which I like quite a lot, and I think that they have done a lot to make Rust a language which is possible to do quite a few functional things in. But when it comes to their asynchronous support, they have just added async await, and I think that's a serious mistake. I don't think it's a good fit for functional, and I don't think that they spent enough time considering other options. Anyway, so vthreads are great. As of Java 24, they are now pretty good as they stand, but there are still some more things coming. So for the final part of the talk, let's talk about the future. So what's coming? Well, truly final fields, stable values, Project Amber, a bunch of other things. Project Amber is one of the long-running projects that OpenJDK has had. It's also the one which is mostly completed. So there's not much left of Project Amber. We have text box, we have switch expression, we have instance solve, we have the first bits of pattern matching and records and sealed types. All of these things are in the language today. What is happening? What's coming next? Well, we're going to complete the pattern matching story. Further releases of Java are going to complete what pattern matching looks like for us within the language. We do not get anything new as a final feature in Java 25, unfortunately. So there is nothing between 21 and 25 that's going to go final for pattern matching, which I think is it's a bit disappointing, but I understand why we are where we are. I'll talk about Project Valhalla in a sec. We were just talking about Project Loom. The further deliverables for that are really three things: scoped concurrency, scoped values, and stable values. So structured concurrency is a new API, which is about thread handling and grouping. It's about saying this bunch of tasks go together and they need to cooperate to achieve a goal. It works by creating a scope, you fork off concurrent subtasks, and then you join the entire scope together when you're done. So a piece of simple code will look like this. The API for this changes in Java 25, but this is what it looks like as a 24 in preview. You create the scope, and you can see this is a try with resources, just like we always do in Java. We look at getting some sentiment and some, and then fork this off into a separate subtask. So we have these two subtasks, which are represented as fSentiment and fDelta. They go off and run, presumably on background threads across the network. They come back, join, throw if failed, and then we return back our result here. I'll skip the examples, they're in my slides. So that's great. We also have scoped values. Now these things are effectively almost like a modern replacement for thread local. They allow you to take a value and bind it to a specific thread in just the same way as you do with thread local. So you have this variable, and you say within this thread, it takes this value. It's immutable. Once you've bound it, you can't unbind it, and you can't change it in that thread. But what you can do is you can create a new subscope, and you can rebind it in the subscope. There's no way to leak this. There's no way to change the code. You can't change the value from far away by leaking a reference to the scoped value like you can with thread local. So it's, generally speaking, it's better, it's more predictable. It's easier to work with than thread locals were. If you've written any Scala or any language which has implicits, then this is sort of Java's take on implicits, but it is deliberately very controlled and locked down. I think that the initial versions of Scala, especially Scala 2's implicits, allowed interesting functional approaches, but they came at a big cost. So I actually prefer the way that we do it with scope values. Okay? So these are not a replacement for thread local, but you might find that they're a better fit. Retrofitting these when they're available, and these will be final in 25, might be an interesting use case for you. The other way that you can think about them is as a dynamic scope, which Java has not had up until now. Dynamic scopes are not that common in programming languages. They are found in Lisps and some shells, and also in Perl. But the standard scoping that we've typically seen is what we call lexical scoping. So if you've experienced the need for a dynamic scope, here they are. This is a piece, the stable values, on the other hand, these are preview. They are a way of providing a constant value which is immutable once created, but they are lazy. They don't initialize until you are ready for them. So unlike final fields, you don't have to initialize them when the value becomes visible, and the idea behind them is that they are a step towards final, really genuinely meaning final. As you know today, I hope, if you have a final field, you can mess with it using e.g. reflection. With these things, and with the truly final fields approach which is coming, you won't be able to. So with scope values and stable values, we are getting pieces of lazy evaluation, and we are also closing the door on some of the nasty tricks that people used in the past. Finally, Project Valhalla. This basically, hands up if you know what Project Valhalla is. Only a few people, I think more people did. Okay, so this basically it's a huge change which is coming in Java. It's been under development for over 10 years, and it basically is a way of unifying the type system. Primitive types and objects will now be thought of in the same way. And the way that we do that is by introducing a concept called a value class. And a value class is one which does not have identity. You know, we're always used to the fact that Java objects have identity. They live in the heap. We can point at them, and the pointer points at the start of the Java header. That memory address represents the identity of the object. And we know the difference between .equals and equals equals. Value objects are ones which do not have identity. They do not have a header. They have only final fields. They do not have identity or synchronization. What this means is that we are able to produce things which are usable more like primitive types. So for example, in Java, we don't have 128-bit integers, right? But we could. And we don't have a 16-bit floating point number, which the machine learning people and those data scientists would really like us to have, but we could. So those are the sorts of things which Valhalla will enable. It bridges the gap between primitives and objects. It enables you to do deconstruction and reconstruction, and it also will potentially fix some of the things that people complain about with generics. Because with the unification of the type system, you will be able to do things like have list of int. There will also be null fixes. So the folks that were talking about null safety in Kotlin, Java is getting null safety as well. That's at an early stage, and there are things that can be done to help with it. So if you want to hear some more about that, come and ask me afterwards. But yeah, Valhalla is exciting. It's moving towards completion. It's not coming in any form in preview, even in 25. So where are our updates? The API change to structured concurrency means we don't get structured concurrency in 25. We do get scope values and stable values in preview, but no Valhalla roadmap. So returning to our principles, outcomes, not mechanisms for functional programming. Does it matter? And the perfect is the enemy of the good. So is Java a functional programming language? Well, does it matter? It's a useful language with more functional features than it used to have? And does it allow you to write functional code? Depends on your style and what you want, the sort of functional code you want to write. I think it does. I think the path is looking good, and the perfect is the enemy of the good. So thank you very much. I am over time for questions, but if there was one person, otherwise you can come to the book signing and ask me questions there. And should we have a look? Should we see how we did on the donation drive? Because here's one I made earlier. Oh, come on, you can do better than that. Oh no, the Wi-Fi was down. Okay, well, in which case, I'm going to put the QR code up. You can still take pictures of the QR code and donate later. Thank you very much, everyone.